Good evening, everyone. Welcome to NPTEL tutorial session for the course Essentials of Oxidation, Reduction, and Carbon-Carbon Bond Formation Application in Organic Synthesis, taken by Professor Yashwant D. Vankar, retired from Chemistry Department, IIT Kanpur. So this is our ninth tutorial session. So far, we have been discussing till week 8 lecture contents, and we have also solved several problems related to those topics, and we have also solved till week 7 questions, week 7 assignment questions. So today, in today's session, we will be firstly discussing week 8 lecture contents, and then we will go on to the discussion on week 8 assignment question. We will wait for a couple of minutes to see anyone is joining, or else we will start. So, in the last lecture, we have seen sharpless epoxidation, its mechanism, how it is working, and how this allylic alcohols can be converted into enantiomerically pure epoxides by using tertiary butyl hydroperoxide, titanium tetraisopropoxide, and either diethyl tartarate plus derivative or minus derivative at minus 20 degrees Celsius using molecular sieves as well, 4 angstrom molecular sieves. And we have seen how minus DET will give a particular enantiomer, while plus DET, that is LDET, will give other enantiomer. And this also we have seen the selectivity epoxidation from alpha side is favored when this type of orientation exists, and opposite occurs with the case of minus DET. Now we have also seen the kinetic resolution, so we can use kinetic resolution using this sharpless asymmetric epoxidation to separate uh, asymmetric compounds from a racemic mixture. So now we will see what is pine rearrangement. So pine rearrangement is the utility of epoxide via epoxide ring opening. So what is happening in pine rearrangement is that, so in the presence of a base, this alcohol proton will be abstracted, and that is attacking over, that is opening this epoxide, forming this particular epoxide. So then nucleophile will attack at this position and open this epoxide to form this compound. So mostly in the case of terminal epoxides, normally the nucleophiles add to the terminal carbon and we will get this particular compound. So that is known as pine rearrangement. So another example, another reaction is Katsuki-Jacobson's epoxidation, where asymmetric epoxidation of simple unfunctionalized olefin without any hydroxy group in the vicinity. So in sharpless epoxidation, it needed an allylic alcohol to favor the epoxidation. But in this epoxidation, there is no such hydroxy group in the vicinity, and it is carried out using this type of silane complexes. Now, how this is prepared from this diamine complex and this aromatic compound in presence of K2CO3, we will get this imine, that is this aldehyde and this amine derivative. So the two molecules of this aldehyde is reacting with one molecule of this diamine compound to give this compound imine derivative. Then that in treatment with this manganese triacetate, it will give this compound which is the catalyst. Then this upon treatment with PIDA or NaOCl, like any oxidizing agent, will oxidize this manganese to get this active catalyst. Now, how to prepare this particular compound? So, yeah, for preparing this second compound, what we need is just this phenolic derivative and using this hexamethylene tetraamine type of compound, and the second step with H2SO4 we can get this compound. So how it's happening? Firstly, this one will get protonated to form this intermediate. Then this nitrogen lone pairs will fall over here, and this will stabilize the positive charge on nitrogen to form this iminium ion, and that will react with this particular alcohol. So this oxygen lone pairs will come over here to form the ketone, and this is attacking over this imine carbon, and this positive charge on the nitrogen will be stabilized to form this particular compound. Then what is happening? This is getting isomerized or converted back into the phenolic derivative to form this compound. Then again, what will happen? This NH is getting protonated to form this one, and then this particular nitrogen lone pairs will fall over here, and this bond is breaking to form this particular intermediate. Then again, this nitrogen lone pair will fall over here, and this proton is taken by this carbon, and this will shift over here to form this particular intermediate, which upon hydrolysis will give here aldehyde, that is our desired compound, and this will be the byproduct. So here, depending on which diamine we are using, so depending on that, we can either get SS isomer or RR isomer. So SS isomer will give one particular epoxide, and RR isomer will give another particular epoxide. So from this particular RR intermediate, we are getting this catalyst, and from this compound, we are getting this particular catalyst. Now this is the mechanism how this is working. So if in the case of this particular catalyst, this is the favored attack because this is not favored because of the steric reason. Similarly, this is also not favored, and here also this tertiary butyl groups doesn't allow this attack as well. So here, as we can see, this phenyl group and this methyl group is above and this phenyl group is below, so this attack is favored, but from this phase it will not be favored. So left side attack is favorable with a stipulation that RL group remains away from the bulky of the group. So considering the steric factors, this will be favored and the product will be this particular epoxide. So these are some of the examples of how each epoxide is formed from different catalysts. So this is SS catalyst. So here, as we said, this is not favored due to bulky group. Here also not favored due to the bulky tertiary butyl group. Here also same thing. And here, if we consider this is the favored attack here, and this is SS. So this R group is tertiary butyl group or TIPS group. So that's why this three attacks are not favored and only this attack is favored. So mechanism is like this. So Mn, this is the active catalyst species, so that will convert this alkene into this epoxide, and then this phenyl this phenyl iodo, that compound we are using, that is converted into this phenyl iodide also. So the oxygen is coming from this compound to the manganese to form this active catalyst species. Now, in another perspective, we can say Jacobson explains it in this way that axial hydrogen pushes the bigger phenyl group on the other side. So, if the hydrogen is in axial position, it will not favor that attack through that side. It will be attacking from the other side. So, that is shown here. Here, this hydrogen is axial, so this side attack is not favored. Here this hydrogen is axial, so this side attack is not favored. So two different catalysts, SS and RR, but both Katsuki and Jacobson arrive at the same conclusion. So Katsuki explains an attack via the imine moiety. So this attack via the imine moiety is also favored due to pi pi interaction between incoming alkene and the imine group. So this side is less favored, either this side or this side is more favored due to the interaction with this pi electrons of this imine and that of the alkene. Then this we already saw how this is prepared. So this is another example for another type of catalyst where salicylaldehyde derivatives are difficult to get. So phio is not a practical source of oxygen, so instead of that people use NaOCl as well. Then additives such as amine N oxides like NMO, PPMO, that is 4-phenylpyridine N oxide, are used to increase the rate, yield, and enhance selectivity. So these compounds act as axial coligands and also stabilize manganese 5 oxo complex. Then electron donating group at the para position stabilizes this manganese 5 oxo complex, and the rate of oxygen transfer is decreased, implying late transition state. Increasing the alkene interaction with silent ligand is more important. Now, this is another method to prepare that other than from that imine derivative. This is another method to prepare this particular compound. So here what is happening, this paraformaldehyde and this monomeric aldehyde will react with this phenol to form this particular compound in the presence of MgCl2, and then in the presence of triethylamine it will interact with the ketone and form this compound. Then upon releasing this CH3O minus and MgCl will form this aldehyde, which upon hydrolysis will give this phenolic aldehyde. Now these are the examples for this reaction. So here if we see this compound, this upon treatment with this Jacobson's condition, we are getting this epoxide, and then when we are using this nucleophile, it is attacking and over the here at this SN2 fashion and opening the epoxide to form this compound. Then here also catalyst RR is used and we are getting this epoxide. Then NH3 is attacking over the center to form this particular compound, which can be written like this, which can also be written like this. Here, as we see, ester is the smaller group than the phenyl group. That's why it is attacking from this side over this side. Now this is another example. So here CO2 IPR appears to be a larger group than aromatic group. So we are getting this particular compound which is used in the synthesis of this diltiazem, which is a hypertensive agent. And apart from cis disubstituted olefins, even trisubstituted olefin give epoxide with high enantiomer selectivity. Then this type of compounds can also be used for kinetic resolution also. So here racemic one we are taking, and only one particular compound is converted into the epoxide and the other remains as such. So here also same, if we are using SS catalyst, only one will be getting converted into the diol by epoxide opening, the other epoxide is remaining intact, and so we can use it for kinetic resolution as well. Now, if we see the mechanism, cis selectivity in cis 1 to disubstituted alkene suggests that the reaction proceed via a concerted 2 plus 1 pathway. So, like this pathway, it can form, or a metallo-oxene intermediate, that is through a 2 plus 2 pathway. So in if it goes through here, we will be getting cis 1. If it goes through this radical intermediate, we will get this trans product. And if it is going through this manganooxide, again we will be getting cis product. And through radical we can get cis product, and if it is rotating we can get the trans product as well. So in many conjugated alkenes, formation of a mixture of cis and trans epoxide suggests that it is proceeding through this radical pathway. So only through the radical pathway there is a possibility of trans and cis product. If it is through 2 plus 1 pathway or 2 plus 2 pathway, it will be giving only the corresponding cis product. So the cis trans ratio is found to be dependent on the oxidant which we are using, additive and catalyst in some cases. Now, if we see these examples, in all these three cases, we are getting 100% cis isomer only. So, change of oxidant leads to ring open product, but the epoxide is still cis. So, this leads to a suggestion that the reaction may proceed via a metallo-oxidate. Now, next reaction was asymmetric dihydroxylation using stoichiometric osmotic hydroxide, which was used originally. So, this is a very reliable dihydroxylation. Even tetrasubstituted olefins react easily. And if we use amines or pyridines, it increases the rate probably by forming electron-rich complex with osmotic hydroxide. So the original dihydroxylation reaction using stoichiometric amount of osmium tetroxide was expensive, volatile, and toxic, with the result that even small scale reactions were also inconvenient. Now, this dihydroxylation shows specificity for double bonds and has no particular substrate requirement, which is also one advantage of this dihydroxylation using osmium tetroxide. And over the years, the original dihydroxylation procedure has been modified to operate catalytically more rapidly and in better yield. So, since this osmium tetroxide usage in stoichiometric amount is expensive, co-oxidants were used. So, examples are osmium tetroxide and this NaClO3, sodium chloride, or this osmium tetroxide H2O2 condition, Miller's reagent. But in this case, over oxidation also occurs. Now, this Sharp Plus introduced this combination of osmium tetroxide and this tertiary butyl hydroperoxide along with this tetrabutyl ammonium hydroxide or tetraethyl ammonium acetate, or this NMO, that is N-methyl morpholine oxide, was used as a co-oxidant. It is known as Upjohn dihydroxylation as it was developed by Upjohn Company in 1976. So these are some of the C2 symmetric bidentate amine ligands which assist this osmium tetroxide mediated dihydroxylation reaction. So 99% enantiomeric excess was observed for trans stilbene, but it is not used in catalytic amount in terms of ligands and osmium tetroxide. So this bidentate ligand gets bound to the osmium very strongly. So but too loose complex will not give high enantiomeric excess. So in this regard, a cinchona alkaloid based ligands along with this NMO gave the best results. So that was this dihydroquinidine and dihydroquinine. So these are pseudo enantiomers as they are not enantiomers but act as though they are enantiomers. So here only 0.13 equivalents of this particular ligand NMO is needed in stoichiometric and 1.2 equivalent osmium tetroxide is needed in 0.2 percentage. So we will be getting the desired product with catalytic amount of osmium tetroxide and ligand. So stoichiometric to catalytic and enantiomeric excess was 94 percentage. Now, this was due to the secondary catalytic cycle that the enantiomeric excess was dropping, in which ligand was not involved in the secondary catalytic cycle. So, this NMO convert osmium 6 glycolate to osmium 8 glycolate along with the expulsion of the chiral ligand. So, this osmium 8 glycolate, which is not having the chiral ligand, also carry out dihydroxylation with some of the olefins leading to low enantioselectivity. So this is the mechanism in which we said this osmium 8 glycolate with the chiral without the chiral ligand can also undergo this epoxidation, dihydroxylation, and that will give the less enantiomeric excess in overall. So, in an attempt to improve the enantiomeric excess, four substantial developments were made. So, the osmium tetroxide, osmium 6 is getting converted into osmium 8 by this NMO. So, instead of NMO, if we use this K3FeCN6 K2CO3 using tertiary butanol in H2O, generally increase the rate of the reaction, and a new class of dimeric ligands with two alkaloids combined through a spacer unit was used, and then a more convenient source of osmium 8, that is this potassium osmate dihydrate, was also used. So these are the structure of the thylacine, pyrimidine, and intoline ligands which are used in this sharpless asymmetric dihydroxylation, and this is the final ligands which we are using currently, that is AD mix alpha and AD mix beta, which is DHQ, 2 PHAL, and this potassium osmate, potassium ferricyanide, and K2CO3, and this AD mix beta, this is DHQD, that is quinidine derivative. One is quinine and other is quinidine derivative. So this depending on the phase of this beta phase hydroxyl group and alpha phase hydroxyl group attack, we will be getting different products. So low rate of reaction was observed for trisubstituted olefins, which was due to the slow hydrolysis of osmium 6 glycolate, but the hydrolysis could be increased up to 50% by adding this methyl sulfonyl amine, which helps in regenerating the catalyst and at the end of the catalytic cycle. So this is that modified condition by using this as well. So without any ligand, we are getting 1 is to 2 and diastereomeric ratio of these two compound. With this DHQ twice PHAL, we are getting 10 is to 1, in which this is the major one, and with DHQD PHAL, we are getting this one as the major one. And this is another this is used for the synthesis of this plus castanospermine. Now this is Glaxo's asymmetric synthesis of this camptothecin. So here this particular compound upon dihydroxylation and then the oxidation of this anomeric alcohol using iodine calcium carbonate will give this compound, and which is used in the synthesis of this camptothecin, which is an anti-cancer drug. Now, this Royal Swedish Academy Nobel Prize for 2001 was for this asymmetric catalytic asymmetric synthesis. One half of the prize money to William S. Knowles, Ryoji Noyori, and the other half to this Barry Sharpless. So this was for chirally catalyzed hydrogenation reaction, and this was for chirally catalyzed oxidation reaction. Now, the first industrially catalytic asymmetric synthesis contribution of Knowles, and Knowles' aim was to develop an industrial synthesis of rare amino acid L-DOPA, which had proved useful in the treatment of Parkinson's disease. So, this is the L-DOPA that catalyst for using asymmetric hydrogenation with enantiomeric excess of 95%. So now we will move ahead with this hydrogenation of ketone. So now we will go ahead with the assignment question. So the first question was the major products A and B formed in the following sequence of reaction. So this particular compound upon treatment with this tertiary butyl hydroperoxide D minus DET, titanium tetraisopropoxide molecular sieves 4 angstrom will give A, which upon treatment with this dimethylamine and sodium hydroxide will give this B. So which is the corresponding A and B? So here what is happening is that this D minus DET will allow epoxidation from top side as we said earlier, and since it is a trans-cinnamic alcohol, the choice 3 is the correct one. So this is the correct answer. And now paint rearrangement followed by epoxide opening with this SPH minus is happening to form this product or this product. So it is, this can be written in this way as well. The absolute configuration of the two chiral centers are RR, and thus the choices are 1 and 4. So this can be or this can be. So the correct answer would be option A. Moving to the next question. In the following sequence of reactions, A and B are respectively. So here is one this epoxy alcohol, which we are treating with this methyl chloride and pyridine will give this A. Then upon this B condition, it is giving this product. So which will be the corresponding A and B. So here, what is happening? The correct answer is option 4. So firstly, in methyl chloride and pyridine condition, this will be converted into corresponding mesylate, and then this lithium diphenyl cuprate can replace this methyl group with this phenyl group to give this product. Now the next question is the major product in the following reaction. So this epoxide upon treatment with this KCN and methanol, which will be the major product here. So here the first one is the correct answer. So nucleophilic attack is happening under neutral condition and the sterically less hindered position, that is this position is being attacked. Since the epoxide is above, the Cn minus is attacking from below and the product will be option 1. The Katsugi-Jacobson epoxidation of Z4-methyl pentene using the following aldehyde and chiral 1,2-diamine and an appropriate manganese salt. The major product that will form this and this will be which one? So this is this chiral 1,2-diamine and this is this aldehyde. So which will be the major product? So here what is happening, this structure of this olefin is as shown below. The isopropyl propyl group is bigger in size than methyl group, so it would prefer to move away from the group of catalyst. So the epoxide, which is 2R 3S2 isopropyl 3 methyl oxyrene, will be the correct answer, that is option 3. Moving to the next question, asymmetric sharpless epoxidation is associated with dihydroquinone derivative, metalloxetine, oxaborlidine, chiral 2,3 epoxy alcohol, tertiary butyl hydroperoxide, secondary catalytic cycle, and paint rearrangement. Which are the correct options here? So here, as we know, this tertiary butyl hydroperoxide is one of the reagents used in asymmetric sharpless epoxidation. The products formed are chiral 2,3 epoxy alcohol, and the paint rearrangement is also associated with that. So the correct answer is 2, D, E, and G. Moving to the next question, one of the main intermediate products in the following sequence of reaction. So here beta pinene upon thermal cracking and then treating with catalytic N-butyl lithium and diethylamine, this is forming. So which is the intermediate of this reaction? So here the correct answer is option 4. This beta pinene upon heating, this bond is breaking and this is coming over here to form this intermediate, which can be written in this form as well. So the correct answer is option 4. 4. Now the next question is the structure of the major products formed in the following sequence of reaction. So this particular compound upon treatment with this dibalate in the first step and then this hydrolysis, then zinc bromide and then hydrogen in nickel condition, which will be the major product. So here, this reduction of this nitrile group with aldehyde to aldehyde will take place with this dibalh H. Then carbonyl ene reaction is taking place and hydrogenation will take place to form this compound option 3 via this particular transition state. So this aldehyde will coordinate with this zinc that will attack over, that will take up this proton, this bond will shift over here and this will attack over this center. Moving to the last question, during the conversion of a prochiral molecule to a chiral molecule in high enantiomeric excess via asymmetric induction using a chiral catalyst, a statement that is correct in this regard is the free energy difference between the two diastereomeric transition states should be as high as possible. There should be no difference between the free energies of two diastereomeric transition states. There is no formation of diastereomeric transition states, instead they are enantiomeric transition states of different energies. The two enantiomeric transition states should be of equal energies. So here the correct answer is answer 1. Since the transition states would be diastereomeric in nature, the only way one can get high enantiomeric excess is via large energy difference between the two diastereomeric transition states, so that one of the enantiomer will be very large and other one will be very less. So, with this, we will conclude today's session. I hope it was clear whatever we discussed regarding the week 8 lectures as well as week 8 assignment question. If there is any doubts or clarification needed, please let me know. So, we will see in the next tutorial session, which will be on next Saturday. So, thank you for joining and thank you for listening.